Hello everyone, welcome to another DaSSWeb. Today it is our pleasure to welcome Peter Flatch as our speaker. Peter is well known in the ML community and doesn't really need an introduction. However, I'll say some words. He's a professor of artificial intelligence at the University of Bristol since 1997. Is internationally recognized expert in the evaluation and improvement of machine learning models, with significant contributions in the fields of highly structured data mining, explainable AI, and data science methodology. He has authored influential books, including Machine Learning, the Art and Science of Algorithms that Make Sense of Data, which has become a key reference in the field and has been translated into many languages. Peter also served as editor-in-chief of the Machine Learning Journal and has held leadership roles in various prestigious conferences and organizations. He has a strong track of records of collaborations, both in academia and industry. Peter, thank you very much for accepting our invitation, and the floor is yours. Thank you.
Thank you very much for the invitation. It's nice to be here. If not in person, then at least virtually. As you may know, I was in Porto not long ago, and I've been in Porto many times. So today I will talk about explainable AI, and let me share my screen. There we are. That should be shared now. So actually, this is an in-browser presentation. You see a URL at the bottom there. If you go there, and you'll see an outline of my talks, and this talk is there as well, so you can independently follow the slides in your browser and also follow up on some of the links that I put there. So today I will talk about explainable AI. And this is essentially, so this is the outline of the talk. This is a version of a talk I gave in Lisbon, actually, last year at the first XAI conference. But the fifth point is new. That's a paper we presented 2 weeks ago at the European AI conference in Santiago de Compostela, which is not quite Portugal, but not very far from it. So okay, let's get started. So what is explainable AI, and what do you need to know there? So a lot of the work, and I'll reference the people who were doing the main work there, but a lot of the work was driven by my PhD student and later postdoc Kasper Sokol, and he has the following slightly abstract definition of explainability. So explainability is the process of deriving understanding, some extracting meaning through reasoning applied to transparent insights distilled from a data-driven predictive system, and those insights are adjusted to the explainee's background knowledge. So that's quite a mouthful, and we're not going to dwell on this too much, but there's a couple of important aspects there, which is that there is an explainee. You're explaining to somebody. There is some reasoning involved, and there's also the background knowledge of the explainee that's relevant. So you're trying to come up with an explanation for an explainee that makes sense in the context of their background knowledge. So that's kind of quite an abstract and complicated point of view. Now here is actually a very simple point of view, which is a simple geometric view, how it might look like in classification. So what you're looking at here is a very simple two-dimensional feature space. And we have in black, we have a decision boundary separating two classes. And the black vector is the weight vector defining the decision boundary. So that's the vector pointing in the direction of, let's say, the positive class. Then in red, we have a feature vector that so we have an instance that we want to explain why is this instance currently on the negative side. And so we will be talking about methods like lime and shap that get feature importance out of these classifications. So the answer that a method like lime or shap gives is these features are most important, are contributing most to the classification of that instance. But there's another thing in blue that is also important. This is sometimes called the recourse or the counterfactual. So the blue dotted line basically tells us what would need to change for the classification to potentially change from negative into positive. So, for example, the standard example here is people, somebody applies for a loan at the bank and the bank denies the application, but then a counterfactual would be, okay, if your income was, let's say, 5,000 euros more, your annual income, then the loan would have been approved. So it's kind of these kind of reasoning effects are important as explanations. And we'll talk about all these things. So we talk about feature importance, and we'll also talk a little bit about counterfactuals. Right, so the first topic I want to briefly explain is explainable AI for time series. And this is work done by Torti Civil, who was my PhD student here in Bristol, and she graduated, I think, about a year ago. And this was a paper that was published in AI Stats, and there are some further links there to the paper, to the GitHub site, and also to Torti's presentation at AI Stats, because this was still the tail end of the pandemic, so that was an online conference. So why is time series a particularly interesting case for explainable AI? And this is actually a point that is perhaps not always very much appreciated. So what is a good explanation for one particular type of data? What would be a good method to derive an explanation for one type of data may not be a good explanation for other type of data. Okay, I see a question here. Is there a link to the deck? Let me just very quickly go to the first slide, and there is the link to the deck. I can probably even copy this in the copy link. Okay, there we go. Let's put that in the chat. So if you go to that website and then you have the top link there, that should take you to the current presentation. Right. Okay. Right. So let's get back to where I was. Okay. So Lime, for example, has been developed primarily in the context of images, but Lime for tabular data is a completely different story. And here Torti in her PhD thesis looked at essentially Lime and later also Shapley values for time series. So what's special about time series? So first of all, we need a meaningful concept of super segments. So the idea is that if you're trying to explain an image, you are first segmenting the image in what is sometimes called superpixels or image segments. And you want to say, okay, this bit of the image is primarily responsible for me classifying it as a dog or as a cat, right? So we need to do something similar to that in time series. So we need to be able to segment time series into these kind of super segments, which we use for explanations. And then secondly, we need to be able to switch off segments. So the way that Lime works is that you first segment the image, and then you're taking some of the segments out of the image, and you see whether then the prediction of your model would change, right? So switching off segments in images is doable. There are some questions around it as well, because how, if there is a ball in the image and I take that segment out, I need to replace it with something, let's say with black or with the background color. I will probably still see the ball because the outline is still there. So switching off segments in images is not entirely trivial, but doable. But what are we going to do with time series? So that's a question as well. And then the way that algorithms like Lime work is that they sort of sample in the neighborhoods of those time series and make variants of the time series and see how the predictions of the model then change. And that gives us information about locally what the decision boundary looks like. So we need to be able to do all these things for time series. And I will very briefly walk you through what Torti did here in this application. So for segmenting time series, she actually did something I think pretty clever, and I think this is something that people will be able to use in other applications as well. So what you're looking at here is the segmentation in. So okay, let's look at the blue arrows, for example. So we have on the left, we have 2 points from our time series. And if we do some kind of nearest neighbor clustering, then so we do some kind of clustering, and we find for the top blue line, we find the closest segment, the closest point somewhere else in the time series, which appears further on. And then for the bottom blue line, we do a similar thing, and we find the most similar time point there somewhere else. Now, these 2 points are adjacent on the left. If they're also adjacent on the right, then the 2 left points are in one segment, and then the 2 right points are also in one segment. And this relationship is not really holding for either the green lines and or the pink lines. So for the green lines, even if I start with 2 adjacent points on the left, slightly to the left of the yellow line, we actually end up, the most similar time points are not anymore adjacent on the right. And that tells us something about that there is a change there, and that these endpoints belong in different segments. So the actual algorithm is a little bit more involved than that, but that, I think, gives a very interesting way of trying to segment time series into bits that are kind of locally coherent. So that was her solution to segmenting the time series. Then the next question is, how are we going to switch off a particular segment? And for that, that solution is, I think, kind of fairly obvious. You do some kind of Fourier analysis. On the right, you have a Fourier transform of the original signal. And what you see there, so you see on the left, you have the time domain. On the right, you have the frequency domain. So what you see on the right is that long yellow line shows a kind of background frequency of slightly under 0.2. and then there are other segments which appear and disappear. So you could then argue, this is of course an idealized example, but you could then argue that that constant line is the background frequency. And if we switch off a segment of the time series, then we will replace it not with the flat line, but with the frequency component of that time series. Okay, so the background components are present throughout, and then the foreground components can be switched on or switched off in Lime's sampling algorithm, so that then you have a set of samples, and then you can train a surrogate model locally on that set of samples to find out what the decision boundary looks like locally. And then there are some further questions as to what constitutes similar time series. So actually, again, here we used a solution from the literature, which was then dynamic time warping, which basically means that you treat the time axis as a flexible thing. So what you're looking at here is the beginning time series is x0, and then we have three possible variations. So x1 is simply x0 with a segment removed. Same for x2 with a different segment removed, and x3 actually uses a bit of dynamic time warping, so it's only part of the segment removed, and that is then judged to be the most similar thing. So with these three ingredients, you can actually then start applying Lime to time series, and so Torti applied this to the quite well-known Mimic dataset. I'm sure in Porto, many people have been looking at this dataset. So this is a real-world data set from a hospital, which is the occurrence of sepsis and whether or not that occurrence of sepsis. So this is where your immune system essentially attacks you, and unfortunately, in some cases, this is lethal. In some cases, it isn't, and so. Torti used these kind of techniques to distinguish between those and to come up with explanations for a particular prediction. And then, of course, you have correct predictions, but you also those are the ones on the left. But you also have incorrect predictions. But in both cases, you could come up with an explanation of which bit of the time series would be responsible for that prediction. There's a lot more that I could say about this, but I encourage, if you're interested in this, for people to look at the AI stats paper, or if you wanted to have access to Torti's PhD thesis, then we can do that as well. So that's just one example of how we can take Lime and adapt it to a different data type. So I think there are two things that I would like you to take away from this, which is that approaches such as Lime and Shapley values, which I will talk about in a bit, they are not fixed. Lime is not a fixed algorithm, but it's kind of like an algorithm schema. And for different data types, you need to instantiate the algorithm schema in a different way. It doesn't necessarily generalize as easily. So for example, this idea of switching on and off bits of an image or of a time series is not so obvious in tabular data. So how do you switch off bits of a spreadsheet? That is not so straightforward how you do that and what you would replace it with. So in each of these cases, to make it work, you need to have these kind of, it's almost like plugins to the algorithm schema to make it work. Okay, so next topic I want to briefly touch upon is the topic of counterfactuals, and this is work done by Rafael Poyazzi, who was not my PhD student, but I contributed to this work as well. This was published in, I think, the AI Ethics and Society conference in 2020, which was, I wasn't there, but it was in New York, which was pretty much just before COVID hit, or actually, with hindsight, COVID had already hit, but at that time people were still traveling to conferences. So this is a very nice piece of work, I think, and it's generated quite a lot of interest, and I think partly because the idea is really simple and appealing. So let me remind you. So a counterfactual is you are in one region of let's say in this example, the X is in the blue space, so it's classified as a blue point, and you're asking yourself, how should I change X in order for the classification to change to a red point? That's a counterfactual. And there are four possible counterfactuals are indicated here by the letters A, B, C, and D, and they all have kind of slightly different properties. So the counterfactual A is very close to this decision boundary. So it has, a machine learner would say it has a low margin. So this would be saying, okay, well, the absolute minimum by which your annual salary should be increased is this much, and then you would just about get a loan. So maybe that's not not the best. Maybe you want something a little bit more generous. So that would be B, but B itself is a counterfactual, and it has higher margin than A, but it is itself in a low density region. So while the classifier classifies it as red, it hasn't actually seen many examples like B before. Okay, so maybe you want your your counterfactual to be in a high density region like C. So C is in a high density region. However, in order to get from X to C, you need to cross a low density region. And maybe in order for the counterfactual to be actionable, you want to travel through a high density region as well, so that every time you make a change, it's an actionable change. So that's what the actionable in the title refers to. So that's why we come up with this idea of an actionable counterfactual. D, which is something that has high margin, is itself in a high density region, and can be reached by crossing a high density region. So this is the basic idea. There are some complications in order to make this work. Again, I encourage you to look at the paper if you want to know more. But let me just give a few more examples. So again, this is artificial data. So in this example, what you see here, let me just see if I can zoom into this. So what you see here is a number of different counterfactuals here. So the green points are all counterfactuals found by the algorithm. So initially there is a path going from this point X to at the top, going down, and then the path kind of bifurcates, because then we have different options. So there are always they're usually not a single counterfactual. There are different ones that the algorithm finds. And here's an example. No machine learning talk would be complete without an MNIST example. So MNIST is handwritten digits, numbers. So here you could ask yourself, okay, my starting point is a 0. How would I need to change the image to change the prediction to 8? And what you see in these two rows is two ways in which I can travel through the handwritten digit space to finally convert something from a 0 to an 8. And these are sequences that are found by the face algorithm. So that's my my second example. So let's carry on and let's talk a little bit about XAI tools. There's a lot here, and again, I will just give you some pointers for you to look at. And a lot of this work was done by Kasper Sokol, and we got some funding from Thales, and this led to a number of things. One of them is a toolbox called Fat Forensics. So it's concentrating on explainability, but FAT stands for fairness, accountability, and transparency. So you could say that explainability is something that you want to achieve because it gives you transparency. So Fat Forensics is this toolbox. So let me see if I can bring it up here. Let me see, this must have gone somewhere in the top. There we are. Okay, so Fat Forensics, this is the toolbox. So it's got a lot of documentation there and examples and tutorials. And it's basically a Python library that you can explore at your leisure. So, for example, here are so using grouping to evaluate fairness of data and models, explaining machine learning predictions, that's Lime and counterfactuals. And then you basically have notebooks here where I'm just looking. Yeah, so this is the well-known iris data set. So basically, here's an example where we have petal length and sepal length here with the three classes quite well separated, and then you have the point here to explain, and then the counterfactual. So if I travel from this cross to the yellow cross, then the classification would change from setosa to versicolor. Okay, so again, there's a lot of material here, and it reinforces this idea that there are different ways in which you can do this. There are different sampling strategies, there are different similarity metrics, and so on. So, and this is all implemented in this toolbox, which you can explore at your leisure. Going back to the presentation, so there are some other papers here. So there's a paper here in the Journal of Open Source Software. There's a paper here in the Software Impacts paper. And the idea is that we are building on functionality that comes from scikit-learn, for example. So we have our data in a 2D array. We have all the machine learning methods that scikit-learn offers. And then on top of that, we have the explainability primitives, and then we build that up to versions of Lime, for example, and finally we have a presentation layer where we can, for example, visualize our explanations. And another part of this work is something that we call Blimey, which stands for Build Lime Yourself, but Blimey is actually a kind of native English speakers or native British English speakers would know this as a term of surprise. And this takes this idea of modularity, is that you can build your own version of Lime as long as you have a way to sample data locally, you have a way to form these interpretable representations like the segments in images or time series, these superpixels, and you have a way of generating explanations of that, then you've built a version of Lime yourself for a particular type of data, and so there is an associated GitHub website there and a paper if you want to explore that further. And last but not least, and this was actually also published in AI Ethics and Society, or maybe it was actually published in the let me just check that. Yeah, I was wrong, actually. That's not AI Ethics and Society. That was published in the Fat Star conference. Back then it was called Fat Star. Now it's called, I think, FACT, Fairness, Accountability, Transparency. So that's, this paper is about the idea that it's kind of similar to the kind of fact sheets or cards that you have with foodstuffs, for example. So in the EU, if you buy food, then you can see, how much salt does it contain and what percentage of the recommended daily intake of salt does it represent, and the same with sugar or carbohydrates and so on. So the idea of explainability fact sheets is essentially to come up with a language to describe an explainability method. So what properties does it have? So for example, what kind of data type is it applicable to? Is it model agnostic, or does it make certain assumptions about the model? How has it been validated? And so on. So this is actually let me just have a quick look at oh, that doesn't work. Okay, that's a link that I need to fix. But we can have, in the paper, there is a lot of supplementary material about what, examples of. So for example, the paper contains a fact sheet for Lime itself. So what are the properties of Lime? And so if you build a variant of Lime, then you can use these fact sheets to change how to indicate how it differs from standard Lime. Because just to make a point on that topic, I think we have often a situation where people use a name for something. So two people may call the same thing Lime, but it may be actually a slightly different algorithm. And to actually emphasize that point, if you go to the GitHub website associated with the original Lime paper, the code on the GitHub website is not exactly the same algorithm as is in the paper. So that's already an issue. This is why we need these kind of languages describing more clearly what does it do. Is it the original vanilla version? Does it contain some changes and some updates, or some regularizer or whatever? So I think because it's now so easy to obtain code or to make a variant of something, we really need to keep track of what these different whether these versions are different versions and how they differ and so on. So that's kind of where this comes in. Okay, and finally, and this is going to be my last topic, and then I'm very happy to open things for questions. This is the paper we did recently. This was actually presented at the European AI conference in Santiago de Compostela 2 weeks ago. So this is about Shapley values rather than Lime. So this work was led by Paul Gauthier-Noé, who actually visited Bristol for a month, funded by the Taylor network. And so Taylor was one of the AI networks funded by the European Commission. Very successful. It has now finished, but one of the things that they did was fund mobility and visits. And so this was a very successful visit. And so we came up with this idea of explaining multi-class predictions. So what is this about? So this is actually the paper in a nutshell. So what you're looking at, imagine there is a 3-class problem. Actually, this example could be iris. So let's say that it's iris. And what we have here is 3 directions. So we have the 3 classes are indicated by the orange, blue, and green vectors. So for example, the green vector points down, the orange vector points to the northwest, and the blue vector points to the northeast. So why do we have this kind of 2D space if it is a 3-class problem? Well, the space you're looking at is a Euclidean space which is derived from the probability simplex. So so if you have a 3-class problem, then every prediction is a 3-component probability vector, but it sums up to 1. So even though in the 3 simplex, you have 3 probabilities, you only have 2 degrees of freedom. And sort of this idea of 2 degrees of freedom is captured in this Euclidean space. It's called an Aitchison geometry. The details are not very important, but this is a very nice space to work in because the simplex is actually not very easy to understand because it's not really additive. You can't really add up probability vectors in the simplex. You need to, for example, multiply them. Whereas in this space, everything is additive. So what you're looking at is the red dot is the base prediction. So this is an idealized example. So imagine that if I average all my predictions over all my instances, I get a uniform distribution. So that's what you're seeing here. These 3 bars close to the red point are a uniform distribution. So if I average over all instances, my prediction will be uniform. And that is actually equivalent to the origin of this Euclidean space. And now we have 3 features, and they are indicated here by phi1, phi2, and phi3. So we have 3 features, and what you see here is that the phi1, the first feature, pulls us slightly away from the origin in the direction of the green class, right? So there is a histogram associated with phi1, which actually gives the green class the highest bar, the orange class the lowest bar, because we're being pulled away from the orange class, and the blue class is in between. And then so this is essentially, in a multi-class setting, the Shapley value for that first feature. So that first feature is now pulling us in the direction of the green class. Then the second feature pulls us horizontally, and horizontally basically means that it has no effect on the green class, because the green class, in order to increase or decrease the green class contribution, you need to go up or down. So if we stay horizontal, the green class stays the same, but we're moving further away from the orange class, and therefore we get a larger contribution of the blue class. And in fact, we end up in the blue class decision region, right? So now, if I add the second feature, then the blue class would be the prediction. And then finally, the third feature pulls us back again to the green class. And actually, because we're now on the negative y-axis, this tells us that the contributions for the blue and orange class are uniform. Now, of course, there is no order in features, so I could have drawn the features in a different order. I could have started with the third feature and then the second feature and then the first feature, but because this space is additive, we will always end up in the same point. So this is the kind of multi-class explanations that we can obtain with our model, and we call it Shapley compositions. So the Shapley value is not a single scalar value, but it's actually a vector. So why couldn't we do that before? Well, originally Shapley values are work with binary classification problems. So we only have two classes. And this is coming straight from the figure is coming straight from the SHAP library, which is an implementation of Shapley values. And what you see here, there is a base value, which in this case is about 1/3 for the class that we're talking about. And then the features pull us in the direction of a much lower value. So in this case, those 4 features sort of decrease the prediction for the class that we're looking at. And what we've done in this multidimensional space. So let's look at the example on the right first. So what we're looking at here is still coming from the SHAP library, but they're doing one versus rest. So the top figure says, can you come up with an explanation why this example is classified as setosa rather than the other two? And how do the features influence that? The second figure down asks the same question about versicolor. So can you tell me how the features contribute to observing a higher value for versicolor in contrast with the other two classes? And then the third figure does the same with Virginica. The thing is that looking at this thing, it's very hard to see what a specific feature such as petal length, what is its overall contribution? Because in the bottom figure, petal length decreases the value of Virginica, it increases the value of versicolor, and it decreases the value of setosa. But as you see, you really need to, they're not plotted in the same space in these 3 diagrams, and that requires a lot of reading into these figures. Now, conversely, this is what we get with our method. So we have the base value here, which is slightly away from the origin. And then we have our 4 features, and we show very clearly of each feature, we can clearly see the effect that it has on all of the 3 classes. And also we see very clear, we have the norm of these, we can calculate the norm of these vectors, which tells us something about the influence of that feature. If the change vector is if the norm is very, very low, then it doesn't have a huge overall contribution. So this is, we would argue, more easily interpretable. It's properly multi-class, and we don't have to do this one versus rest decomposition. Okay, so what about more than 3 classes? So let's look at the bottom one here. So again, this is an MNIST example with some features that we constructed, which again is, I think, some segmentation of the pixel space. So we have 10 classes here, numbered 0 to 9. We have 6 features here, and as you see, feature 1. So these are the the individual feature compositions to the class. So so they're not stacked together at the moment. They're just looked at as individual feature, and you see immediately that feature 1 and feature 3 pull very clearly towards the green class, which is the number 2. And everything else looks like a bit noisy. So maybe feature 4 and feature 6 pull us towards class 5, but it looks pretty noisy. And this is immediately obvious from these histograms. And finally, we also have a visualization where this is a bit like parallel coordinates. So here we look at the cumulative effects of all the features. So we start with the base value here, which is not quite uniform, but close to uniform. And then we have ordered the features on the norm of their Shapley vectors, and you immediately see that feature 1 pulls us towards the green class, feature 3 pulls us a bit more towards the green class, and then basically the green class stays constant, and something happens with the other classes, but you see immediately what is happening here and how the different features contribute. So I think as an explainability tool, this is pretty good, and it wouldn't be it would be very different if you would need to look at 10 one versus rest graphs, as you would have to do in the SHAP library. So there is also we're still working on that, but there is also a GitHub library, and we want to incorporate this into the SHAP library. Okay, so let me start wrapping up then, and in a moment open the floor for questions. So really, the take-home messages are these. So I've said it already. Approaches such as Lime and SHAP should be considered algorithm schemas. They are not fully developed solutions for every type of data. We may need to change some of the plugin elements to make it work, like we did for the time series. And there are, the devil is in the detail here. So it's not a solved problem. Even if you say we apply Lime for explainability for your particular type of data, you may need to change things a little bit. Second point, again related to this, there is this kind of habit, people sort of saying, oh, I give an example for image data, but it also works for tabular data, or for text, or for speech, or for music, or whatever. And this is often not so straightforward. If you have things like we're doing some work here in understanding, coming up with explanations for music, for example, and music is something, obviously it's a sound file, and it has frequencies and so on. But if you convert it to things like spectrograms, then you have 2D images again, and that kind of works. So often you can use explainability techniques from images, also apply it to music represented as images, but that doesn't work for everything. So it doesn't necessarily work for if your data is about molecules. You shouldn't expect that if you convert a molecule to an image, that somehow you can apply the same technique. So you should expect that things that work in one data type may not work for another data type, and there is a lot of focus on images, but I think in day-to-day domains, tabular data is actually much more prevalent and much more important, and that needs more research to work on explainability for those. And finally, we need to take probability seriously, and that last paper was an attempt at doing exactly that. In the end, what we want to explain is not just a classification, but we want to explain a probability vector. Yeah, why does the learning algorithm come up with this probability vector? Probabilities live in the simplex, but with the kind of transformations that we studied, and this comes from a field called compositional data analysis, we can move the simplex to a Euclidean space, and that's actually a nice space to work in, and because probabilities itself are not linear, they're not additive, but they can be converted to a linear and additive space. And I think the technique that we use there can be more broadly applied. Some mention and thanks to the sponsors of this work. And finally, just to repeat that this is work by a lot of people who we've had the pleasure to collaborate with here in Bristol. And here are pictures of all of them. And with that, I'm going to stop and give you the opportunity to ask questions. Thank you.